All right, let's dive into the world of topological quantum computing,
Mhm.
specifically these Majorana zero modes, MZMs, these mysterious particles that everyone's saying could completely revolutionize computing as we know it. You sent over some research on measuring MZMs.
Mhm.
Sounds like a big step towards making these stable quantum computers everyone's dreaming of a reality.
Yeah, it's definitely groundbreaking. We're talking about a potential massive leap forward. I mean, imagine a quantum computer that's practically immune to errors. The possibilities are, well, a bit mind-boggling, to be honest.
Before we get ahead of ourselves, maybe just back up for a second. Remind me, what is it about these MZMs that make them so special? What is it that makes them different from your average particle?
They're definitely not your average particle. You can think of them kind of like particles that are their own antiparticles, and they exist at the edges of these, well, they're called one-dimensional topological superconductors,
Yeah.
1DTS. And the thing is, what's really fascinating is that, well, they have this non-abelian nature.
Non-abelian nature.
Yeah, it's a bit of a head scratcher,
Mm.
but what it means is that the way their quantum state changes when you swap their positions, it's unique. It's like, I don't know, braiding them together.
Yeah.
And that braiding, that's what makes them so robust against
So
errors.
you're saying the information isn't stored in the individual MZM, but in the way they're linked together? That's pretty wild.
Yeah.
But then the challenge is, how do you actually measure the state of these MZMs? That's where this research comes in.
Exactly, yeah. The paper lays out a new method for measuring what we call fermion parity, basically whether there's an even or odd number of MZM. So think of it like the 0, 1, or your topological qubit. And they've managed to do this all in a single shot, which is a huge improvement in speed and accuracy.
They use something called an interferometer.
Right.
I'm picturing a giant machine, but I know
Oh,
that can't be
yeah.
right.
Not giant, no, but it is cleverly designed. So it involves a superconducting nanowire made of indium arsenide and aluminum, and that's where the MZMs live. And they've coupled this with quantum dots. They act like tiny islands for electrons. And then by applying a magnetic field, they create these interference patterns that reveal the fermion parity of the MZMs.
So they're using these electrons to kind of spy on the MZMs. That's
Yeah.
clever. So what did they actually observe in the data? What did that look like?
Well, what they saw was really interesting. A signal that was switching randomly between two distinct values, almost like, I don't know, watching the qubit flip a coin. Heads even parity, tails odd parity. And that random switching, it's a clear sign that the system is behaving quantum mechanically.
And that randomness, that's not just noise, right? That's a real part of the quantum world.
Exactly. It's a signature of the qubit fluctuating between its possible states, which is what you want to see. And what's even more impressive is, well, they measured the average time between these switches. They called it the random telegraph signal time. And it turned out to be on the order of milliseconds.
Wait, milliseconds? Isn't that a long time in the quantum world? What does that tell us about how stable these MZMs are?
It's a good sign. A really good sign. Because remember, one of the big challenges with quantum computing is keeping those qubits stable for long enough to actually do computations. This research, well, they showed a poisoning time. That's the time it takes for the qubits information to get scrambled, and it was way longer than in previous experiments.
So we're seeing stability, which is a big deal.
hmm
But there's always skepticism in the scientific community. I mean, were there any doubts about whether these signals were actually from topological MZMs?
Well, there were definitely some alternative explanations, like maybe the signals were from these things called Andreev-bound states. Those are also found in superconducting systems.
So how did they respond to that? Did they convince the doubters? How did they make sure it wasn't just Andreev-bound states?
Oh, they took a very rigorous approach. They didn't just say, trust us. They showed that the signals had this very specific dependence on the magnetic field, like a fingerprint almost, that matched what theory predicted for MZMs, but not for these Andreev-bound states. Plus, they ran simulations. Simulations that accounted for the effects of Andreev-bound states, and those simulations couldn't replicate their experimental results.
So it's like they said, if it were Andreev-bound states, this is what we'd see, and we don't. That's pretty convincing. But I remember reading that, well, even if the states weren't perfectly topological, they still met some pretty strict requirements. What did they mean by that?
That's important. It's really hard to just come out and definitively say you've got topological MZMs. So they were careful. They acknowledged that, there could be subtle effects they hadn't accounted for, but they showed that the states they observed, they had properties that were incredibly close to what you'd expect for topological MZMs.
So they're saying it's either topological MZMs or something we haven't even thought of yet.
You got it. They set very strict limits on the possible energy splittings of those states, so they ruled out most non-topological explanations.
This is all really fascinating, but how does it all fit into the big picture? I mean, how does this research actually bring us closer to building a topological quantum computer?
That's the big question, isn't it? Let's talk about that.
Okay, so it sounds like they've made some real progress, not just in measuring MZMs, but also providing evidence for their topological nature. But I'm still trying to wrap my head around how this all translates into actually building a quantum computer.
Yeah, it's I guess, the big question, right? This research, well, it clears a major hurdle. It shows us we have a reliable way to read the state of these topological qubits. And not only that, it does it really fast. It's like we're laying the foundation for a whole new type of architecture.
So it's not about building one today, but more like opening a path to a better future for quantum computing, a more stable one,
Stable.
scalable.
Exactly. Think about it. They achieved a signal-to-noise ratio of 1 in 3.6 microseconds. I mean, that means they can determine the parity, the even or odd of the MZMs, so basically the state of the qubit, and they do it with high accuracy, and all in a really short time.
So this single-shot measurement, it could be a game changer.
Yeah.
But how do we actually go from measuring these, I don't know, exotic particles to actually doing computations with them? That seems like where things get tricky.
It's definitely complex, but the key is in the braiding of the MZMs. We talked about that earlier. Remember, they have that non-abelian nature, so if you exchange their positions, you get unique and predictable changes to their quantum state.
So it's almost like we're choreographing a dance for these particles. Each move represents a logic operation or something.
You got it. These braiding operations, they allow us to manipulate the information stored in the topological qubits so we can perform computations. And the cool part is these operations are inherently resistant to noise because they're based on, well, the global topology of the system, not the specific locations of the MZM.
So it's all about how they're linked, not where they are. So we're encoding the information and how they're linked, and then manipulating that information by moving them around, like some kind of quantum knot puzzle.
Exactly. And that's where the scalability comes in. If we can develop more sophisticated techniques to control, I mean, really control and braid these MZMs, we could theoretically scale these systems up. We could make much larger, more powerful quantum computers.
Okay, so now we're talking. That's the exciting part. What kind of problems could we solve with a topological quantum computer that are just completely impossible with even the best supercomputers we have today?
The possibilities are huge. And honestly, we're just scratching the surface, I think. One area that has a ton of potential is drug discovery. Like, imagine if we could simulate how molecules behave at the quantum level. We could actually see the interactions between atoms and electrons that control chemical reactions.
So no more trial and error, just pure computational design. We could create drugs for anything.
Well, that's the dream. We could design drugs from scratch, really target specific diseases and with amazing precision. Maybe create entirely new classes of drugs, ones that could tackle diseases that are incurable today. And not only that, but understand how they interact with the body, minimize those side effects, really maximize how well they work.
That's incredible, like personalized medicine taken to a whole new level.
Yeah.
Almost sounds like science fiction. What about material science?
Right.
There have to be huge implications there too, right?
Oh, absolutely. With a topological quantum computer, we could design materials that have never existed before, materials with totally unique properties that could lead to breakthroughs in, well, everything, energy storage, electronics, you name it. Like, imagine superconductors that work at room temperature. That would revolutionize our energy grid. Or batteries that could store energy for weeks, all on a single charge.
Wow. It's hard to even imagine what that would look like. And what about cryptography? I mean, quantum computing, it has the potential to completely break the encryption we use to protect data online, doesn't it?
That's a real concern, yeah. And it's something researchers are really working hard to figure out. But the good news is, well, topological quantum computers, because they're so robust against errors, we could use them to develop completely new encryption methods, methods that are resistant to quantum attacks. Like, well, fighting fire with fire.
So it could break our current security, but then give us the tools to build something even better.
Yeah.
That's fascinating. But let me ask the practical question. How far away is all this? How long until we see these applications in the real world? Are we talking years? Decades?
It's hard to say. It really is. Because even though this research is a huge step, there's still major challenges. We need to get better at controlling those MZMs and braiding them. And we need to figure out how to scale these systems up to create larger, much more complex quantum computers.
So no topological quantum computers in our homes anytime soon.
Probably not. But the progress is really remarkable, and the whole field is moving incredibly fast. It's definitely something to keep an eye on.
Before we get too lost in the future, I want to go back to something. We talked about how this interferometer works, but I'm curious, how did they actually measure those interference patterns? What were they looking for specifically?
That's a great question. They use this technique called dispersive gate sensing. What it does is it measures the quantum capacitance of one of the quantum dots.
Quantum capacitance. Okay, you're going to have to break that down for me.
It's actually not that complicated. Basically, it's a way to measure how the charge on the dot changes when you apply a voltage. And the thing is, that capacitance, it's directly affected by the fermion parity of those MZMs.
So they're not actually seeing the MZMs themselves. They're just seeing how they influence the electrical properties of this tiny dot.
Exactly. Think of it like, I don't know, watching ripples on the surface of a pond. You're trying to see the fish underneath, but you can't see them directly. So you watch the patterns they create, the ripples.
That's a great analogy. So the clarity of those ripples, the strength of the signal, that's what's so impressive about this research.
Right. They could clearly see these jumps in the capacitance signal as the parity of the MZMs flipped. It gave them a high-fidelity readout of the qubit state.
It really is a remarkable feat of engineering, and just the ingenuity of the experiment itself is impressive. It never ceases to amaze me, the creativity and persistence of these researchers,
Yeah.
really pushing the boundaries of what we know.
I agree. It's truly inspiring, and it shows you that scientific progress, it really comes from this combination of, well, deep theoretical understanding, really clever experimental design, and that willingness to explore the unknown.
I'm definitely excited to see what the future holds for topological quantum computing. This research has opened my eyes to just how much potential this field has.
I feel the same way. I think we're really at the beginning of a technological revolution, one that could reshape our world in ways we can't even imagine right now.
Before we wrap up, is there one key takeaway you want to leave our listeners with?
I think the most important takeaway is that, well, topological quantum computing isn't just some theoretical idea anymore. It's a field that's advancing so rapidly, and we're starting to see real progress towards actually building these machines.
So anyone interested in the future of computing should definitely be paying attention to what's happening in this space. It
Yeah.
could be a real game changer.
Absolutely. And on that note, I guess I'll leave our listeners to think about a world where quantum computers are as common as our smartphones. What would that look like?
That's a great image to leave everyone with. Until next time, keep exploring, keep learning, and keep diving deep.
Yeah, it's crazy to think we might really be on the edge of, I don't know, a whole new era of computing. One where these quantum computers, they're not just theoretical, they're actually real.
It is a big shift. And this research, well, it shows just how much progress we're making. But I do think it's important to remember that, well, we're still just starting to understand what topological quantum computing can really do. So it's not just building like faster, bigger computers. It's about changing how we even think about computation, right?
Exactly. I mean, quantum computers, they work so differently from classical computers. It's like they're using these, I don't know, bizarre laws of quantum mechanics so they can tackle problems that are just impossible for even the most powerful supercomputers today.
So it's like we're discovering a whole new language, a new set of rules for how to process information. Okay, so if we're talking about topological quantum computers, how are they different from the, I guess, the more common types of quantum computers people are building?
One big difference is how fault-tolerant those topological qubits are. Because the information, well, it's not stored in the individual states. It's encoded in how those MZMs are linked together. So they're really robust. I mean, incredibly robust to noise from the environment. That's a huge advantage over other types of qubits. Those are much more sensitive to errors.
So we're talking about a quantum computer that's not only more powerful, but also more reliable. That's amazing.
It's definitely a major goal. And the other difference is scalability. With topological quantum computing, well, we have a way to make larger and more complex systems. We can do that by braiding more and more of these MZMs together.
So we're using these, I don't know, super resilient building blocks, braiding them together into these complex structures. It's kind of like quantum weaving or something.
Yeah, that's a great way to think about it. And as we get better at controlling and manipulating these MZMs, well, the possibilities just become, I don't know, almost limitless.
This has really been eye-opening. I mean, this whole deep dive, I feel like I have a whole new perspective on the future of computing. I bet our listeners are feeling the same. This is definitely a field to watch.
I agree. It's incredible to see the progress that's being made, the implications for, well, for everything, for science, for technology, even society as a whole. It's huge.
Well, on that note, I guess we'll leave our listeners with, I don't know, just the thought of what a world transformed by topological quantum computing would even look like.
Until next time, keep exploring, keep asking questions, and keep diving deep into this incredible world of science and technology.